everyone, I'm Shambhavi Mishra, a PhD student at ETS Montreal, and today I will be discussing our research on Do Not Trust What You Trust, Miscalibration in Semi-Supervised Learning. This work is in collaboration with Bala Murali Murugesan, Ismail Benayat, Marco P. Russoli, and Jose Doles, and it was accepted at TMLR. Let's start with the problem at hand. Semi-supervised learning methods, especially those based on pseudo-labeling, often improve accuracy but degrade model calibration. This was the first observation we had. The primary cause of this degradation is that pseudo-labeling tends to favor overconfident predictions. This results in miscalibration as seen in our reliability plots when compared to the supervised baseline, which was trained on the same amount of label data as the other three state-of-the-art methods: fixed match, flex match, and free match. In our another observation, we found that pseudo-labeling minimizes min-entropy. This is crucial because SSL methods aggressively minimize min-entropy for most unlabeled samples, which is a stronger push than what's offered by Shannon entropy. To elaborate further, minimizing min-entropy pushes uncertain predictions towards overconfidence, reinforcing early mistakes that are challenging to correct. Compared to the Shannon entropy, the min-entropy is more aggressive in the gradient dynamics, particularly at the beginning of the training where most predictions are uncertain. This dynamic explains why pseudo-label SSL methods often exhibit worse calibration than their supervised counterparts. In the third plot, we have the ratio of samples with the same hard prediction for weak and strong augmentations that were above the selection threshold for the three relevant SSL methods. Let's get back to this plot after understanding how we can generalize the loss in these SSL methods. The total loss can be broken down into two components: the cross entropy based on the labeled samples and the pseudo cross entropy on DU, which is your unlabeled data samples. Further, we can disintegrate this DU into two parts, D dash and D double dash. D dash is essentially the samples where the weak augmented predictions did not coincide with the strongly augmented images prediction, whereas on D double dash they coincided, leading to the min-entropy term. We empirically observed that the amount of samples where the argmax of the predictions from weak and strongly augmented versions was the same is that D double dash was significantly larger than those with different predictions, that is D dash. This figure here emphasizes on the same observation. In particular, as shown in the figure, and after some iterations, more than 80% of unlabeled samples included in the training shared the same pseudo-label between weak and strong annotation, regardless of the approach we analyze between fixed match, flex match, and free match. Moving further, another significant issue we identified is the generation of overconfident predictions in pseudo-label SSL. We noticed larger logit magnitudes for both correct as well as incorrect predictions even when compared to the supervised baseline, which means that now even wrong prediction come up with very high confidence. Now let's discuss our solution. We propose imposing a penalty on logit distances. The non-linear ReLU penalty prevents logit distances from exceeding a predetermined margin M. The intuition behind this penalty is simple. For logits where the distance exceeds a certain margin, we backpropagate a gradient to decrease those values. This helps reducing overall logit magnitudes, potentially alleviating the miscalibration issue in the training set of unlabeled samples. Here, lambda is a blending hyperparameter which controls the contribution of the cross entropy loss and the corresponding penalty. These results highlight the impact of our approach. In the kernel density estimation of logit distribution for a specific target class, which in this case is 5, our method has noticeably improved calibration. Moreover, we can see that even for non-target classes, our approach leads to a reduction in logit magnitudes, indicating reduced overconfidence. Moving forward to the results, we observe that in 16 out of 18 different settings, adding the penalty brings improvement gains compared to the original version of each method. Note that these gains are sometimes substantial, improving the original method by up to 4%. For example, fixed match with CIFAR 100 dataset when only 200 labels were used, as well as Eurosat dataset for flex match as well as fixed match. Similarly, including the penalty term systematically enhanced the calibration performance of the three analyzed approaches, whose improvements are typically significant and are up to 6 to 7% in several cases. This was our contribution to improving the calibration in semi-supervised learning. Thank you so much.